Okay, let's do a little testing here. I can always cut the beginning off. Okay. All right. Let's see. First of all, I'm going to. Hello? Oh, I didn't plug that in either. Okay, now we got it. Do I have a calculator on here? It's a calculator. Okay, I guess I should do a calculator too if well, I don't need to. Okay. So select all the tables. Okay. Question 1. Select all of the following tables which represent y as a function of x. Okay, I know if the table represents a function of x that I cannot have any x values paired with more than one y value. So -1 is paired only with 0, 1 is paired only with 2, 4 is paired only with 2, 9 is paired only with 8, and 15 is paired only with 11. I don't see any ordered pairs that have, I don't see more than one ordered pair with the same x values. Okay, so no repeated x values. Okay, so that first one is definitely a function. The next one to the right says -1 is paired with 0. X value of 1 is paired with 3. 4 with 5, 8 with 7, 13 with 12. So again, I don't see any ordered pairs there that have the same x value and a different y value. Then bottom left, you have 0 with -4, 2 with 3, 6 with 4, 7 with 8, and 2 with 3. Now I do see two ordered pairs that have the same x value that are listed in this table. So I see the x value of 2 twice in the table, which usually indicates that it is not a function. But just to be sure, let's make sure that the value of 2 is paired with more than one y value. So that first ordered pair with an x value of 2 shows that 2 is mapped to a y value of 3. And the second ordered pair that has an x value of 2 also maps to a y value of 3. So even though on first glance it may have appeared to not be a function, it actually is. This last one here has, my eyes went straight to the two ordered pairs that have an x value of 3. One of them is paired with a y value of 1, and the other x value of 3 is paired with a y value of 5. So those are two different points with the same x value. So that last table would not pass the vertical line test, and that is not a function, so I won't select that one. Next question, number 2. Select all of the following tables which represent y as a function of x. So now I'm going to look at each one of these graphs and see if there's any vertical line where more than one point would lie on the drawn part, the blue part. So with this first one, I don't see any vertical lines that hit more than one point on the blue line at a time. So that one's a function. Same with the one to the right there. Also the slanted line. Of course, this one here with the ellipsis. You can see vertical lines, several vertical lines that would go and touch more than one point. For instance, the vertical line that goes through x equals -1 will touch at y equals 3 and at y equals 1. So we do have the x value of -1 mapping to more than one y value, and that one's not a function. The horizontal line passes the vertical line test, and this last one, I can pick, let's see, again, the line going through, the vertical line that goes through x equals -1 would touch the graph in more than one place, so that one also is not a function of x. Here in this one, we want to select all of the tables which represent y as a function of x and are 1 to 1. So we're looking for both the x values to be unique and the y values to be unique. So I do notice that that first table has two ordered pairs that have an x value of 8, so that one's not a function. And well, I should go on a little further to say the 8 is paired with a y value of 6, and also x equals 8 is paired with a y value of 12. So that one's not a function at all. The next one down shows 1 paired with 4, 8 paired with 6, and 11 paired with 6. Now, although that is a function because each individual x value maps to only one y value, there are two x values that map to 6. So that means that even though it's a function, it's not 1 to 1. And the last one here, 1 maps to 4, 8 maps to 6, and 11 maps to 12. So in this case, we have each of the x values being unique and each of the y values being unique. So there are no problems with monogamy there. So that last one is the only one that is both a function and also a one-to-one function. Question 4, select all of the following graphs which are one-to-one. So once again, we should be looking first to see if each one of these passes the vertical line test, and if so, it would be a function. But if it's going to be a one-to-one function, it would also have to pass the horizontal line test. So this one passes both the vertical line test and the horizontal. This one doesn't pass the vertical line test, so it's not a function. The next one passes both. The next one after that, this one is a function, but it doesn't pass the horizontal line test, so it's not a one-to-one function. The next one down is parabolic, and that passes the vertical line test. And the very last one here does not pass the vertical line test, so it is not a function. Uh-oh, I missed one here. See, what does it say? Select all the one-to-one functions. I don't see where I went wrong here. Oh, this one's not one-to-one. That's right. It does not pass the horizontal line test. The parabola. Parabolas are not one-to-one functions. Then the next one, based on the table below, we're going to find f of 7. So what we're going to do is we're going to look at where the x value is 7 and see what the y value is that it's paired with. So that's the answer for the first part. Now for the next part, we are told that f of x is equal to 6, and we're told to solve. So what you could do is you could, if it helps you, you could rewrite this as f of x. So we'll write it as it's given first. Now you can replace the notation f of x with y, and then that might help you understand that if you were doing a table of ordered pairs and you knew that the y value is 6, you would be looking to see what the x value is that gets paired with that. So we're going to go in and find where the y value is 6 in the table, and then see that the x value that corresponds to it is 1. And notice that you can only do that second part if it's a one-to-one function. If it was not a one-to-one function, you would have some difficulty deciding which y value or which x value would go with that y value. All right, question 6. Now we're asked a similar question, but this time instead of working from a table, we're working from a graph. So in the first part, it says evaluate f of 1. F of 1 equals what? So another way of writing that is to say that y is equal to 1. So then what is x equal to? Okay. Oh no, I'm sorry. That's incorrect. Oh, girl, almost told you the wrong thing. So what I should have been saying is that the x is equal to 1 because that's the part that's inside of the function. So that's the input. And remember that the output would be the y value, which would be your f of 1. That's what we're actually looking for. So we want to go onto the graph where x equals 1 and follow it to the actual drawn function and see what the y value is there. The vertical location is 2 there. So in other words, if I were to write down the ordered pair 1, 2, right, that's your y value right there on that location of the graph. The second part is where we have to say that y is equal to 1. So then what is the x value that would be paired with that? So going on to the graph where, in other words, y equals 1, what is the x value? So here's where y equals 1. So I'm going to follow that over to the drawn graph and see that the point right there has the coordinates 4, 1. So that's the answer for the second part. All right, and still another question that is similar is instead of being given a table of ordered pairs, or instead of being given a graph, we are given the equation of a function. F of x equals 2x plus 2. And in part A, we're asked to evaluate the f of -4. So all you do is take your function equation, and where you would normally have x, replace it with the value -4. And that's going to, when you simplify that, it's going to reveal your y value. So 2 times -4 is -8 plus 2 gives -6 for the first part. And for part B, we are supposed to start with f of x equals -8. So f of x, I'm going to write the function again, and then I'm going to replace the f of x part with -8 because it says f of x is equal to -8. So I can write -8 instead of writing f of x. Then I can solve for x. And that's why the directions are a little different for that part. Notice that for part A, it just said evaluate because all you're doing is plugging in the x value and then doing the mathematical operations to simplify. But for part B, notice that the directions say solve because once you replace the f of x notation with -8, the next step is to solve for x. So that's what we're doing next here. We're just going to start doing inverse operations. Let's do that. -2 here. We're subtracting 2 from each side to 0 it out from the left. Then we're doing simplifying. And now we'll continue solving. We're going to divide both sides by 2. So we're just trying to get x alone so that we end up with x equals -5. Okay, so that's the answer for that part. Okay, now we're looking at some graph pictures and matching each graph with the corresponding function type. So for this one, you should be allowed to use the Toolkit Functions handout, and that would be in lesson 9. Okay, so here are all the different functions. Wait, why did that happen? Oh, I guess what we need to do is bring this out. And then over here, this isn't what I want at the moment. I want the other thing, this thing. Okay, so now I have my, you can see the different pictures there. Over here I have the reciprocal function, so that's the first one. This shape looks like a V, so that would go along with the absolute value function. The next one looks like parabola, so that'll be quadratic. This one looks like a square root one. This one looks like a cubic. And this one looks like an identity function. Okay, so we're just getting the basic shapes. That's all we're doing there. All right, let's go back to using the note space in case we need it. We might not actually. But what I noticed for this one is we're asked for the domain and range. So when I'm thinking of the domain, I'm thinking about the horizontal locations of where the drawing begins and ends. So farthest to the left, I see the closed dot at x equals -3. So I'm going to start my domain with a square bracket and -3. Then I notice that the graph continues smoothly and continuously all the way until it hits here where there's an open circle at x equals 2. So I'll use the parenthesis since that's an open circle. We're not including that value there. Now for the range, I'm going to be thinking about the lowest it goes and the highest it goes. So the lowest that it goes at that closed dot is at y equals -5. And the highest value for y here is 4. And that is also, even though I don't see a closed dot, I also don't see an open circle. So I'm going to assume that's being included as well. So we'll use a square bracket. All right, this one we're asked to find the domain of the given function given as an equation. Now, the only x values that you cannot plug into a rational function means that it's a fraction with variables in the denominator. And so we have to be careful that the denominator can never equal 0 when we plug in values of x. So I'm going to take that denominator and say, to help me figure out which x values would cause the denominator to be 0. So I'm going to say that the denominator cannot be 0. That's how I'm going to find the restricted values, meaning where I have to eliminate possibilities from the domain. Because we always start with the entire x-axis in both directions, and sometimes we have to eliminate certain sections of it. So starting off with all real numbers, we're going to see if we have to exclude anything. So I'm going to exclude the things that would make that equal 0. So which values would make this equal 0? I'm going to factor it out. And notice that 14, I can find that with 2 times 7. And since this is a positive, I know my signs have to both be the same in my two binomial quantities. And since the middle term has a negative, I know those two signs must be negative. And then if I set each one of those equal to 0 and solve, I'm able to discover that x should not be allowed to be 2 because that would cause the whole thing to equal 0. So I don't want to allow that. And similarly, I shall not let x minus 7 equal 0. So then we should not let x equal positive 7. Okay, so just doing, if I go through all the steps, I would be adding 7 to both sides. And that gives me this, which I do not want to allow. So in other words, instead of saying the whole number line is safe, I'm going to say there's a restriction at x equals 2 and at x equals 7, right? And so turning that into an interval notation, I'm going to say, well, we can start from negative infinity and go up to 2 and not include it. Then after 2, I can go as far as 7 and then jump over that, pick up on the other side of 7 and continue to positive infinity. So just notice that I'm putting a union symbol wherever there's an open circle or wherever there's a value that I need to exclude from the real number line as options for plugging in x, right? So I can go to my interval menu and start putting in negative infinity to 2. Then with a union, I'm going to go from 2 to 7. Then union 7 to infinity. Okay. Given the function, now we are given a piecewise function, and we are asked to calculate the following values. So first, f of 1. So with our piecewise function, which says it has two pieces, it says you use 7x plus 4 whenever x is less than 0. In other words, negative x's. Okay, have to go into this piece for calculation. And the other piece is 7 times x plus 8 whenever we have 0 or a positive, right? So I'm going to notice that the first part says to calculate f of negative 1. So that goes with the first piece. So I'm going to be plugging negative 1 in to the first equation, which is negative 7 plus 4, which gives me negative 3. Now, the next part says f of 0, so that's going to be the second part. And notice, I'm not going to even bother writing it out because when I plug 0 in, 7 times 0 is 0, and 0 plus 8 is just 8. That one's a little too easy for me to spend the time writing out. The next one is f of 2, and f of 2 is also where x would be greater than 0, so I'm going to use the second part. And so plugging in 7 times 2, I'll get 14 plus 8, which is going to be 22. All right, next question. This function graphed above is, and then it wants the intervals of increasing and decreasing behavior. Well, reading it from left to right, I see that it is decreasing from the left to the right and up until where this point is. And this point appears to be right between negative 3 and negative 2 on the x-axis. So I'm going to say it's decreasing on the intervals of x from negative infinity up to negative 2.5, looks like. But then it's also decreasing over here where it starts, it looks like at about 0.5. So I'm going to union this and go from 0.5 towards positive infinity. So for those intervals of x, my function is decreasing. And then where it's increasing is from the interval starting at negative 2.5 and going all the way up until positive 0.5. All right. All right, this one, not bad. Might seem a little intimidating, but it's really quite easy if you understand how to read function notation. So that first part says f of 27 plus g of 26. So to get my answer here, I'm going to look up an x value of 27. Remember, what is inside your function notation represents x equals, and then you're looking for the y value that goes with it, right? So if I go to x equals 27, I'm going to go in the first table because the first table is the one that has f. And where x is 27, the y value is then 4. So I'm going to replace that f of 27 notation with just 4. Now I'm going to do the same thing for the g function. The g function shows an input of 26. So I want to know then what is the y value on the g table. So the table with the g of x function, I'll find where x equals 26 and then look across to where I see its corresponding y value, which is 90. So I'm going to replace g of 26 with 90, and then that simplifies. 4 plus 90 is 94. So that'll be my first answer. Then the next one, g of 25 plus, or no, minus this time, f of negative 10. Okay, so g of 25. What is g of 25? So in the second table where x equals 25, I find that g of x equals 89. So let's replace that. I'm going to subtract. Going to the f table where x equals negative 10, I find that y, or the function value, is 36. So I'll replace that with 36. Then we'll just subtract those, and I will get 53. Okay, next part says f of 27 times, okay, the dot means to multiply. Okay, so f of 27, first in the first table where x equals 27, I find the corresponding function value of 4. Then for g of 25, in the second table where x is 25, I find the function value of 89. So now we just have to multiply 4 times 89, or 4 times 80 plus 9. That gives me 320 plus 36, which is 356. All right, and lastly, we have g of 26 divided by f of negative 10. So first we'll find g of 26. So in the second table where x is 26, g of x, the function value, is 90. So I'll go ahead and replace that there. Then in the first table where x is negative 10, I find that f of negative 10 is 36. And I think 3 goes into both of these evenly, because 90 divided by 3 would be 3 times 30, and 3 times 12 would be 36, so that cancels. Oh, but I think 3 goes in again, actually. Yeah, I probably should have noticed that. So I could either do 3 divided in again to get 10 over 4, which then 2 goes in and I get 5 halves. Or maybe I would have seen that 9 goes evenly into the top and evenly into the bottom. So 90 divided by 9 is 10, and 36 divided by 9 is 4. And then I get, see that those are both even, so you can cut those both in half or divide them each by 2 to get 5 halves. Or I could have seen 90 over 36 as 18 going evenly, and I think that's a little harder to see. Or sometimes you just do, you start doing your, say, where I had 3 times 30 and then over 3 times 12, I could have done 3 times 3 times 2 times 5 over 3 times 3 times 2 times 2. And that would have gotten me the 5 over 2. Okay, so different ways that you can reduce your fractions. Also, if you know how to use your calculator well, there should be a way to transition between decimals and fractions on there. So 5 halves. Okay, 5 halves. Well, also 2 into 5 goes in 4 times, no, sorry, wrong. 2 goes into 5 twice evenly, and 2 times 2 is 4, leaving a remainder of 1. And then 1 over 2 is 1/2, so 2.5 or 2.5, right? So I don't know which one it's going to be. It should be either 5 halves, which usually, oh, here we go. Write your answer as an integer or a reduced fraction. Okay, so yeah, we'll want to enter it as 5 halves then. All right, question 14. Given that f of x is equal to 8x minus 8, and g of x is equal to 4 minus x squared, calculate. Part A says f of g of 0 equals what? So I'm going to start by using my outer function. My outer function here is f. So I'm going to take my outer function and write it down, 8 times something minus 8. So I just rewrote the function without the x in it. Then I'm going to take the g part and put that inside. So the 4 minus x squared is going to go inside because it says g, right? And then because it says 0 instead of x, I'm going to replace it with 0. So now I'll have 8 times 4 minus 0 squared minus 8. So simplifying inside, I have 0 squared is 0. 4 minus 0 is 4. Then 8 times 4 is 32. 32 minus 8 is 24. Okay, so that should be the answer. Now, another way you can do it is you can start with g of 0 and just take your function and get that it's 4, and then come to your second function and plug in 4, your f function, and just plug in 4. So that's another way that you could approach it if you felt like the first way I did it was a little too confusing. You could just do it like this so that you get the same result. Okay, so the first part is 24. All right, now on the next part, g of f of 0, what is that going to be? So again, I can take the outer function to be g. So g was 4 minus x squared. Then the inner part, which is f is 8x minus 8, then I can replace the x with 0 and then evaluate, get 4 minus something squared. So 8 times 0 is 0. Then 0 minus 8 is negative 8. Negative 8 times negative 8 is 64. So I get negative 60. Okay, now if you don't like thinking of it that way, again, we could start with, let's start with f of 0. So the f function, 8 times x minus 8, then plug in a 0 so that we get negative 8 for that part. Then g of negative 8 would be the function 4 minus x squared, plugging in negative 8, which gives 4 minus 64, which is negative 60. Okay, so either way you want to think about it, would work there. Number 15 is, oh, what just happened there? So I was just going to write number 15. Okay, so now we have given the function f of x equals 3x minus 8. Evaluate and simplify the expressions below. See special instructions on how to enter your answers. All right, so down here it says instructions, simplify answers as much as possible. Expressions such as 4 times quantity x plus 2 and x plus 5 quantity squared should be expanded. Also, collect like terms, so 3x plus x should be written as 4x. Okay, good to know. All right, so first it asks for f of a. So f of a means all I'm going to do is instead of writing x, I'm just going to write a. So that's pretty simple. Let's start with that. 3a minus 8. Okay, now next I'm going to do f of a plus h. So once again, I'm going to take the original function and I'm going to put into it the a plus h. Okay, so instead of writing x, I'm just replacing it with the input as it's written there, okay, on the left side. Now, I think we should simplify this. So I'm going to go on and do 3 times a and 3 times h minus 8. And that cannot be simplified any further, but just out of curiosity, if I were to put it in like this, would it be okay? No, it did not like that, but if I put the simplified form, it did like that. Okay, so yeah, so that's that. Then we have f of a plus h minus f of a, and all of that over h. Okay, so while we do have the first part, we have this part right here is that, right? So I'm going to rewrite that, or maybe I could use some colors here. So f of a, I'll write it differently this time. Let's go for it. F of a plus h is all of that. So that's 3a plus 3h minus 8. Then it says minus, right here. So now I'm going to be having something else to put after the minus sign, and that will be just regular f of a. F of a is up here, 3a minus 8, right? So I want to make sure that what I plug in after the minus sign is kept in a quantity for that step. And then I've got the h in the bottom. Okay, so now at this point, we can start simplifying. So I'm just going to rewrite the things that don't need to be simplified any further so far. And then for this next part, I'm going to distribute the negative. So I have negative 3a and positive 8. And when I do that, I see that I end up having a negative 8 and a positive 8 that are going to zero out. I also have a positive 3a and a negative 3a that are going to zero out. And so I'm left with just just 3h over h. So where is my cursor? Oh, here we go. Okay, so now I'm going to write what's left is 3h over h, and then the h divided into h is going to simplify to 1, okay? So I actually just have 3 as my final answer on that last part. Okay, number 16. So now I have f of x, let f of x equal x cubed, okay? If g of x is the graph of f of x shifted up 5 units, write a formula for g of x. Okay, so g of x is taking f of x and shifting it up. So the function values are y values. So if I take this y value and shift it up 5 units, then I'm simply adding 5 to the y value to shift it up. So it's actually that simple that I'm just going to say that if I take the original function, f of x, which it said f of x was equal to x cubed, right? So I have x cubed that I can replace the f of x with, right? So that's going to make this easy. I'm just going to say g of x is equal to x cubed plus 5. All right, now we're going to do some transformations here. What you might want to do is look again at the toolkit functions, because these all look like I guess they look like versions of the square root function. Actually, they're exponential, and that's not on here. So the exponential function is a J-curve. The J-curve looks like so exponential, start with this, exponential functions the basic or the toolkit or the parent function is y, or you could write f of x f of x equals some base to the power of x. So if it's 2 to the power of x, let's say it's 2 to the power of x, right? Then it's going to look like this. And you might want to make a set of x comma y's. And we'll go from, let's say, -1, we'll do 0, we'll do 1, we'll do 2. And so if you put in 2 to the power of -1, you would get 1/2. If you put in 2 to the power of 0, you get 1. 2 to the power of 1 would give you 2. 2 to the power of 2 would give you 4. 3 to the 2 to the power of 3 would give you 8. So that gives you a baseline for where these things are falling. So notice that you have, you always have, like on an exponential function, you always have certain key points, like 0, 1 is always going to be true because 2 to the power of 0 is 1, but also any other base would be 1, right? So this is always going to be true no matter what your base is, right? So in general, whatever your base is, you're always going to have 0 to the power of 1. And you're also going to always have 1 to the power of your base, or sorry, 1 comma your base. So if my base was 3, this point would be 1 comma 3. If my base was 4, it would be 1 comma 4. And so 1 comma the base is another key point. So key points will always be 0 comma 1, and then whatever the base is, let's say the base is here, we're going to have the base comma 1, or 1 comma the base. So those two key points are usually enough to help you figure out transformations or translations of your given function. So notice that here, where the black one is going through the 0 comma 1, so 1 on the y-axis, that would be the original one. And yeah, so that's what it says. So f of x is 2 to the power of x, shown in black. And so the black one is the starting point, the parent function or the toolkit function. And so we're going to see how each of the colored ones could be achieved by applying transformations to the original. So the first thing I notice is the blue one looks like it was flipped across the y-axis. Now when you flip across the y-axis, what's going to happen is any of your values that were over here, any of your points that were over here are going to come here, right? So notice that if this is 1 comma 2, then over here it's going to have to be -1 comma 2. So what's just happened is that the x value is opposite in sign. So it would make sense to choose the option for 2 to the power of -x. So that's, the blue one is 2 to the power of negative x. Then the green one looks like the black one, but flipped upside down over the x-axis. So that one would have a negative out in front of the original function. So that green one, b, should be -2 to the power of x. And that leaves the red one to go along with c, or I'm sorry, that leaves the red one, which is option C, to go along with -2, -x. So what does that mean? And does it make sense? Just to verify it, so taking the original, if I were to change the sign of x, this point would flip over across, right, the y-axis and become a negative x. And then also the y value would switch from being a positive y value to being a negative y value. So that makes sense there, that we would have that shape having flipped both directions, basically. So that it would look like this. But through the point, of course. All right, number 18, the graph of the function 120 over times f of x can be obtained from the graph y equals f of x by one of the following. So whatever f of x is, what's happening here is we're multiplying a number that's less than 1. Another way you could think of that, kind of, just to help you understand, when you're multiplying by a number that is less than 1, you're shrinking vertically. Okay, you're taking your y values and you're making them smaller because, you know, if you have anything less than 1, and really between 0 and 1, because we don't want to go into the negative, that'll end up flipping it. This example is showing us a positive. It's a positive value that's less than 1, or between 0 and 1. So when this happens, you're shrinking it vertically because it's just like, if you could use an example. Let's say I have y equals 2 and I multiply that times 1/2. 1/2 times 2 is going to make it shrink down to 1, right? Whereas if I multiplied that same value 2 times a number that was above 1 or above, well, let's say above 1, let's say 3, that would increase it, right? So you're shrinking when you multiply by something that's less than 1. So 1 over 20 is definitely less than 1, so we'll say that's a vertical compression or shrinkage. Shrinking, compressing is just like squashing it down. So we usually don't say shrinking officially, we usually say compressing instead of shrinking. So that should be, yep. All right, for each equation below, determine if the function is odd, even, or neither. All right, well, there's a couple different ways we could approach this, but yeah, we'll approach it both ways. So looking at f of x first, which is x minus 2 quantity squared, my first thought was that is a parabola shifted to the right 2 units. So that's one where the vertex is on the x-axis at 2. Now just looking at that, if I were to fold along the y-axis, I would not have symmetry. I don't have symmetry across that line. So this one is not even, just thinking about it that way. Also, if I were to rotate this whole picture 180 degrees, it would not look the same. So it's not odd either. Okay, let's rotate the whole picture 100 upside down and notice it looks different. So that one is not odd either. So it is neither odd nor even. That makes it neither. Okay, so that's just, thinking about how things look visually. But if I had to do it algebraically, okay, so I did the visual approach. using my knowledge of how these graphs look, the graph, how to get how the graphs, a quadratic graph, sorry, a quadratic function when graphed, how it would look if I changed it in that way. Now I can take the algebraic approach. So now if something is even, that means it's symmetric across the y-axis. So what does that mean? It means that, let's use one that is symmetric across the y-axis like this. It means that you would have whatever this point is, like say that's 1 comma 1. Over here, you would have the same y value, but an opposite signed x, okay? So that means that by definition, how we write this algebraically is that f of negative x shall give you back the same y value as regular f of x. Okay, so I'm going to take my function, which they said was x minus 2 quantities squared, and I'm going to plug in a negative x and then just simplify it to see if I can get back to the original. So I want to see if after I simplify it, it looks like it should, or as it did when it was given. So let's see what happens if I expand negative x minus 2 times negative x minus 2, and then I FOIL it, I get negative x times x is x squared, right? Because a negative times a negative is a positive, and I get negative x times negative 2 is positive 2x. Negative 2x times, or negative 2 times negative x is positive 2x. And then negative 2 times negative 2 is positive 4. And then I get x squared plus 4x plus 4. Now, if I want to see if it looks like the original, if I were to factor it back out, I would have two signs that are the same, and the middle is positive, so they would have to be pluses. And right then I'm going, oh, well, I would need a negative there in order for it to match. So this is not working out. So it's just not, it's not true. F of negative x in this case does not come out to the original. So that's how we would determine that it's not even by just using algebra. Now, if it is odd, we have a similar way of talking about things. So for odd functions, it'll mean that if you rotate it 180 degrees, something like this is odd. Okay, this is an example of odd. Is this point that's at 1 comma 1, when you rotate to have it look the same, you would have to have both signs, the sign of both coordinates change, and it's still on the graph. So notice that if I take this and rotate it upside down, the picture looks the same, right? The shape looks the same. So that's what happens when you have an odd function. And what we say is it has origin symmetry, or it's symmetric to the origin, okay? Now, in algebraically, we can say that if we change the sign on the x-coordinate, then we should also change the sign on the y-coordinate, okay? And if we're using function notation, then we don't write y, we just write f of x. So that's why you see the negative on the outside of f of x there, okay? So that's what we're checking for. We're checking to see if we take our function which was x minus 2 quantity squared, and we put in a negative x, is the result, which we already worked out up here, and it actually came out to be x plus 2 quantity squared. Is that the same as if you put a negative on the outside of your, is that equal to the original function, quantity squared with a minus out front? And the answer is no. There's no way you could make that happen in this scenario. Like you can't rewrite, there's nothing you can do to mess around with this to get to this result. Because even if you put a negative in there, like let's say I expand this and then maybe I try factoring out a -1. When I factor out the -1, I also end up making my x negative, and only the 2 is supposed to be negative. Likewise, I still have a plus sign here, and even if I tried to also factor out a -1 from that, this is what would end up happening. I would have two -1 factors, so the -1 times -1 would become a +1, and then I would have two matching binomials, so it would be basically just that quantity squared. So notice that the closest I can come to making it look like this result is negative x minus 2 quantity squared, and that's just not the same because again my x variable is supposed to be positive there, right? So there was no way that I could get to this statement to say that plugging in a negative on the x results in a negative on the entire function, on the outside of the entire function. So you might be thinking by now, well, it was a lot easier to figure this out just with the visual approach, right? That was so much easier. So I encourage that, even though you really should know how to do the algebraic approach. In fact, you might be asked to show your work on that, on one of these, but probably one that was maybe a little easier to show out. So let's do g of x now. So g of x is the absolute value of x plus 2. And I'm thinking about the parent function, the absolute value function, which is a v shape. And if it, well, normally it would be at the origin if it was just y equals absolute value of x. So this one has a plus 2 on the outside, so that means it's shifted up by 2 units. So I'm going to just show it, as if it's up 2 units, okay? And then I'm going to notice that it is symmetric across the y-axis. So because of that, I know that this is even. It's even because it's symmetric to the y-axis. Okay, so I already know that using the visual approach. Now, if I do g of negative x, that would be negative absolute value of negative x plus 2. And then what happens when you take the absolute value of something is you're just interested in how far it is from 0 and not interested in the sign. So that's why we say like everything that's inside those absolute value symbols basically comes out positive. So notice here that I'm getting what I started out with, or at least I could write it that way, right? So I can take the fact that I can write this as x plus 2. I could also equivalently write that. I could write x as the absolute value of x, and that would be my original function, right? So algebraically, I've shown now that it's even, an even function, okay? And And if it's even, it's not going to be odd. So once you know that it's one of those things, you can go move on. But notice that you would not be able to say that g of negative x is not equal to negative g of x, right? Because if it was, what is negative g of x going to look like? It would look like putting a negative outside of the absolute value of x plus 2. And if you were to distribute that, you would have negative absolute value of x minus 2. So that's not what we end up with. Okay, so now moving on to the next one, h of x. h of x is equal to 2x minus x cubed. Now, is that even or odd? Well, I'm not sure because I know that if it was just x cubed, that's odd. But I'm not sure about this because it's not a clear shift or multiply or anything like that. So here it's going to be a lot harder for me to tell using, yeah, it's going to be a lot harder for me to tell using the visual approach. You could try doing a table of x, y's and, trying to figure out some points for it. So if I was going to do this in pink, what would that look like? So I could try a few values. -1 would be, -1 cubed would be -1 times -1 would be 1. Oh, no, this is just going to be too annoying. I'm not even going to try to graph it. So what I'm going to do instead is use the algebraic approach. H of x is 2x minus x cubed. So what happens if I plug in negative x? Okay, now this becomes negative 2x, and this this part right here, so I'm just going to write, I'm just copying down the negative that's already there, but now let's focus in on how to simplify this right here. Well, it's going to be negative x because I know that anytime I raise an odd to an odd, I'm sorry, I'll say that again. Anytime I raise a negative to an odd power, the result is going to be negative. So an example to help us think through this could be like -2 to the power of 3. What would happen with that? You would have -2 times -2 times -2. Then -2 times -2 would become +4, but then you would have another negative. So then you would have +4 times -2 gives you -8. So whenever you're raising a negative to a power, if the power is odd, you know you're going to end up with a negative result. So that's why I'm rewriting that as the quantity negative on the outside. That's probably a little confusing. Let's just write it like this. Negative quantity x cubed, okay? Because I want you to be able to see that this part right here is a double negative that becomes a positive. So we can write the next step as -2x plus x cubed. Okay, so now what has happened is both terms that I originally had, here's my original again, right? Here's the original. And here's h of -x down here. And what I'm doing is I'm comparing what's the difference, right? And the difference on my h of negative x is that both signs are different than they were originally on each term. So instead of a positive 2x, I now have a negative 2x, and instead of a negative x cubed, I have a positive x cubed. So that means that I could factor out a negative 1, and so I would end up with 2x minus x cubed on the inside after I factor out that negative 1. In other words, what's happened when I put in a negative on my x is that I ended up with a negative on my entire function. So replacing this part right here with just h of x and putting that negative from here outside of it, you see this is fitting the definition of an odd function. So this is odd, an odd function. This one was neither. Okay, now I've still got 5 questions left, and I've only got I've got less than 3 minutes left, I guess, because I've been explaining everything. So if I go a little faster here, I'm going to try to beat the clock. So if f of x is a linear function and given f of 7 equals negative 8, okay, f of x is a linear function. Given f of, okay, I understand. So what we're being told here is that f of 7 means x is 7, and since the function value is negative 8, I have this ordered pair here, 7 comma negative 8, and then I have an x value of 8 paired with negative 1, so that can be my x2 and y2. And so it said it was linear, right? So then once the slope, which is the difference between the y values over the difference between the x values, so then I'll have negative 1 plus 8 over 8 minus 7, which is 7 over negative 1, and that's negative 7. I'm not going to beat the clock. It might kick me out of here. So to finish showing, and I must have done it too fast too because I was rushing. Negative 1 minus a negative 8. 8 minus 7 is positive 1. I don't know where I got a negative 1 from. So yeah, that should be just regular 7. Then what is the y-intercept? The y-intercept is going to be, there's a couple different ways you can find this. So, so B, that's part A. B, we're going to find the y-intercept. I think when the clock runs out, it might close this on us. So I'm just going to preemptively write down what we have to do for the rest of this. All right, so now the x-intercept. Now we know y equals mx plus b is the slope-intercept form of a line or of a linear equation. So I could write mx plus b here, and I did find the slope already, so I can replace that slope with 7, but then I still need b. I'm also going to write y instead of f of x just to make everything seem easier. And now I can use either one of my points given here to replace the x and the y and then solve for b. Because all I need now is the b for this part. For part b, I need b for part b. And then I need the actual total function. So if I just find b, I'll have the answers for both of these parts. So now I'm going to replace the y and replace the x with the coordinates of one of my points. And it doesn't matter which one I use. For no reason, I'm just going to use 8 and -1. So I'm going to put -1 for y and 8 for x. And then that leaves me with an equation that has only the b to solve for. So that's great. That's what I wanted. I'm going to subtract. Well, first we'll simplify this. 7 times 8 is 56. Then subtracting 56 from both sides, I have -57 equals b. And so let's put that in. Oh, I'm in overtime. Cool. I still have some time here. All right, good. Now, that means that f of x is going to be the slope times x minus the y-intercept, or plus the y-intercept. Okay, 21. This is a piecewise function. So to find the answers for each part of this, I'm just looking for the equations to match each piece from the top to bottom, left to right. So that leftmost piece, I'm going to identify a couple of points on it. Well, really all I need is one point and the slope. So from that leftmost piece, where x is less than or equal to -2, I'm going to pick a point. Let's pick, how about 0, -3? Or I'm sorry, the other way around, -3, 0. That's one point, okay? And then the slope, if I just start at any point and count up and over to another point, so let's say I start at this point here and I count up and over, I'm going to go up 1 and over 1, so that's a slope of +1. And then y equals mx plus b again, where I put in the slope and then simplify. Now I can just replace the y with 0 from this point and the x with -3, and then solve for b so that I get b equals 3. So that's pretty nice. Now I can put that back into my mx plus b. So the first point is going to be x plus 3, the first piece I meant to say. Okay, now the next piece, it's a constant function. I can see that y is always going to be -3, so I can just put in -3 there. But even if I wasn't aware of that fact, if I tried to count the rise over run, notice that I would have to go up 0, and then I could go over as many as I wanted to. In other words, I have a slope of 0, so y equals mx plus b with a slope of 0, with a rise of 0 and say a run of 1 would give me a slope of 0. And if I plug that in, the 0 times x is going to 0 out, so I'm going to end up with y equals a number, right? And then I can see that my, this is your y-intercept, right? Well, on my graph, I can see that the y-intercept in this case is at -3, right? So y equals -3. Okay, now the next part is this part of the line, this line going downwards here on the right. So when x is greater than 1, the piece has the points, let's pick any point, I don't know, let's pick 4, 0. And let's count the slope. So let's just come from this point at right here. If I go down 1 and over 2, so my slope, m, rise over run, is going, had to go down 1 and over to the right 2. So I have a slope of -1/2, so y equals mx plus b, replace the m with negative 1/2, then replace the y with 0 from my point that I chose earlier, and replace the x with 4, and then 2 goes into 4 2 times, or half of 4 is 2, so 0 equals negative 2 plus b. Then solving for b, I'll add 2 to both sides, and I get b equals 2. So that means my line is negative 1/2 times x plus 2. Okay, or at least this part of it is that last piece. All right, now we're matching the graph. Okay, a couple of things that I see. If it was a sad parabola, it would have a negative lead coefficient, and this one has a positive lead coefficient. So I'm only interested in these two options that look like upward-facing parabolas. And then I'm going to look at the fact that when you have something added, well, I'll do it like this. We could even look at vertex form. Let's look at vertex form of a quadratic equation. F of x would be a times x minus h quantity squared plus k. So f of x is equal to, here, 1/3 is the a, and the h would have to be -1, and the k would have to be -3. So my vertex is going to be at -1, -3. That's one way you could figure it out. So if I go to -1, -3, that is this option right here. Another way you can tell is when we learned about transformations in general, seeing it like this, okay, -3. So different things are happening from each part of this graph. So this part right here is going to vertically compress because it's multiplying the y values by something that is less than 1, in between 0 and 1. The +1 on the inside with x is going to move, shift the function to the right, no, sorry, the left by 1 unit. And the -3 is going to shift down because it's subtracting 3 from all the y values. So my parent function, or my toolkit function of a parabola that's just, y equals x, shifted, compressed down, and then shifted to the left by 1. So left 1 would be like over here. Let's do a little better, right? And then shifted down by 3 would bring it down like this. Okay, so that picture was the one I chose. Let me get back to it. Okay. Now, yeah, so that's the one I chose. Shifted happy parabola down and to the left from the origin. Now, number 23, the discriminant of a quadratic equation. Okay, so remember if the equation has how many zeros, it's going to ask us how many zeros, right? So two irrational solutions. Okay, so yeah, we learned this earlier in the course, and it has to do with like what your parabola is going to look like basically. So if I take the example of f of x equals x minus 2 quantity squared plus 1, that one is going to be like this, and it's going to have no solutions, or what we call them when we're talking about functions is no x-intercepts, or even more specific to functions is no zeros, meaning that the function itself can never be zero. Like if you do this, you set it equal to 0, you cannot find any x values that will correspond to a y value of 0, because it's just literally not going to happen. It'll never, in other words, it'll never cross the x-axis. And if you were to multiply this out, you would get that. And so if you were trying to solve the equation x squared minus 4x plus 5 equals 0 with the quadratic formula, you would let a be 1, b would be -4, c would be 5, and you would try to do -4 plus or minus the square root of -4 squared minus 4 times 1 times 5 all over 2 times 1. And what's going to end up happening here is this part underneath is going to end up being negative. So we'll have 16 minus 20, which is -4, and that's 2i when you simplify it. And so what do you end up with here? You end up with two imaginary solutions. I don't know what I just did here. Two imaginary solutions. So x is equal to 4 minus 2i over 2, or 2 minus I, or x is equal to 4 plus 2i over 2, which again simplifies to 2 plus I. So you've got two solutions, and they're different. So they're two distinct solutions, two distinct non-real solutions. So the discriminant is a shortcut to realizing that since you have non-real solutions, they're not going to be drawn on real number lines. So they're not going to show up on the x-axis and y-axis, so the grid or a real number plane. Is that right? Is it plane? No, plane or plane? I can't remember. I think it's okay. So now, all that to say, if we're just trying to get a sense of where our x-intercepts are going to be, you could have realized that, hey, when I do the discriminant, just the part underneath the square root, I'm going to get a negative number. So if I know the discriminant is negative, I know I'm not going to have any x-intercepts because I'm going to have two non-real zeros, okay? And that's why you see for when if the discriminant was -2, you would have two non-real solutions, right? And then other things you can understand about the discriminant, like if your discriminant is 0, then there's nothing after the plus minus, so you just get one real solution. You know, it's definitely going to be real because you no longer have a square root, because the square root of 0 is just 0, and that's a real number. And then since only 0 is coming after the plus minus, we just have the one answer. So one real solution, or one x-intercept, right? So two non-real solutions or zeros, and versus this case. Just one x-intercept. Intercept, which is one real solution or 0. Okay. And then if it's positive and it's not a perfect square, well, then it's going to be irrational. Two irrational. Two x-intercepts, but they're going to be irrational. You can't write them as a fraction or an integer. And if it is a perfect square, then you're going to have two rational. So two x-intercepts, yes, but they're going to be rational. Okay. Then question 24. I don't know if it's gonna like not let me go any further. Okay, 24. Put the equation x squared plus 16x plus 55 into the form. Put this into the form y equals x minus h quantity squared plus k. In other words, complete the square. So you're really just trying to complete the square. So what we do usually is we make sure the lead coefficient is 1, which it is, and then we move the constant out of the way so that we can add in a new constant that'll make this a perfect square trinomial. And that is always half of the middle term's coefficient squared. So I'm going to take half of that, and then I'm going to add half of that squared. And if I'm adding it to the right side, I have to also add it to the left side. So then, simplifying this, I get y plus 9 on the left, and on this side I get x squared plus 16x. Well, actually, I'll just rewrite it. I want it in factored form. I want it as a binomial quantity squared, because that's the whole point of forcing the right-hand side to be a perfect square, because a perfect square trinomial can be factored into a binomial squared. Now, if I bring the 9, if I bring the constant back to the right side, I have my parabola or my quadratic equation written in function form, and I can, it's not only in function form, it's in specifically vertex form, so that I know the vertex is -8, -9, which is helpful, right, if I want to graph it. And then 2 more questions here. So 25, put the equation, no, sorry, write an equation of any form for the equation graph below. Okay, well, I can see the vertex very clearly is, well, first of all, it's a parabola, so I know I'm going to be doing a quadratic function. It's sad, so lead coefficient, when I say sad, it's just a shorthand way of saying it's opening downward. It looks like a sad face. So the lead coefficient has to be negative. I can also see that the vertex is 2, 3. So that's my h and my k, which I can use in vertex form. So, and I also have another point available that's on the intersection of 2 grid lines, so that I can be sure of the exact coordinates. 4, 1. I could also use, oh, it actually has a y-intercept as well, which is convenient. The y-intercept is 0, 1. So now my vertex form of a quadratic equation, which is a times x minus h quantity squared plus k, I can use that here and say that since my h is 2 and my k is 3, I can write it like this. Then I can take one of my ordered pairs, which I might as well take the y-intercept since it's convenient to do so. I'm going to put 0 in for x and 1 in for y. So then I'll have 1 equals a times -2 quantity squared plus 3, which simplifies to 4a plus 3. Then I can solve for a. So I'm going to subtract 3. Why am I solving for a? Because I just need to know what a is to finish my equation of the function. Okay, and then I have 1 minus 3 is -2. Then if I divide both sides by 4, I get -1/2 is equal to a. So now I can come back to my half or mostly done function f of x, or that was y. I had it as y. So I had y is equal to a times x minus 2 quantity squared plus 3. And I'm able to replace the a now with the -1/2. And that's going to be my final answer, or rather just beside over here is what I'll put into the box. And finally, number 26. Consider the quadratic function y equals -x² minus 2x plus 3. The vertex is what point? Now, I could do a couple of things here. There's the vertex formula, which says that x can be found as negative b over 2a. So here my b would be 2, so I could do negative, -2, negative, -2 over 2 times a. A is -1 here. So now I have x, or rather, I should really call this h, because that's the x. That's what we call the x coordinate of the vertex of a parabola in general. And so then I get, simplifying, I get 2 over -2 is -1. So now I know my vertex point has the h of -1. Now to find k, I got to take the x coordinate and plug it into the function. So my function, which is here, is -x² minus 2x plus 3. Then I'm plugging in -1 and simplifying. So -1 squared is 1. -2 times -1 is +2. So now I have -1 plus 5, which is 4. So now I have the vertex point, -1, comma 4. And for the next part, it asks for the equation of the line of symmetry. Well, if you just think about, just do a quick sketch. Say this is -1, 1, 2, 3, 4, and this is 4. Actually, I don't like that at all. Let me make these better. Yeah, so let's do this as -1 here, and 1, 2, 3, 4 here. So if my vertex is here, this is another color. My vertex is here. And I can see it has a negative lead coefficient, so it's going to be opening down. Then the line of symmetry is going to be right through my vertex, right? So what is that line of symmetry? That is where x is always equal to -1. So what you have to get used to realizing is that whatever the x coordinate is for your vertex, that's going to be your line of symmetry, x equals -1. Okay. Now the vertical intercept point, right, which we don't know. Okay, I only did a rough sketch. If I want to know exactly where this parabola is going to cross the vertical axis, then I need to know where is x 0. When x is 0, what is the y value? Okay. So all that means is that I'm going to take my function equation that was given and replace x with 0 and find out that the y value is 3. Notice that the y-intercept is always the constant of the function when it's in this form. So here I know my vertical intercept point has to be 0, 3. The horizontal intercept, which is the x-intercept or intercepts. So remember, parabolas can be floating below or above and not have any x-intercepts. They can be like this one looks like it's going to have two x-intercepts, or it can be where the vertex is actually on the x-axis and it's just going to have one intercept. So this one I know is going to have two x-intercepts, but how am I going to figure out what they are? Well, whatever they are, it's some x value, right, with a 0 for y, and some other x value with 0 for y, right? So then what I need to do is take my function that was given to me and replace y with 0 and solve for x, right? So I'm solving to find x-intercepts is the same thing. Keep going over this over and over. Zeros of the function of the function. In other words, when your y value is 0, what are the x values? Uh-huh, Okay, so I'm solving where I have the y, it told me I was given y equals negative x squared minus 2x plus 3. So y is 0, right? So I'm solving this for x. And I might as well write that this way just because it's something I'm more comfortable with. Doesn't matter at all. Doesn't matter. You can change the side like that. Also, I don't like that hanging negative. Now you could leave it like that and it's not a problem. You'll still get the right answer, but like I don't like it. So if I just divide everything by a negative 1, then I'll get a positive x squared plus 2x minus 3 equals 0. And for some reason, I just like that better. Does it matter? No, really, it doesn't. Honestly, it doesn't. It's just a habit that I have because if I was going to do something like try to, yeah, I'm going to go with it. I'm going to go with it. I'm going to keep it like this. I just, because maybe I want to try to factor it. Sometimes factoring is easier, but when you have a hanging negative and negative lead coefficient, it's not easy to factor. So I'm just changing the signs of each term, and I can do that because, you know, it's set equal to 0, and 0 divided by negative 1 is still 0. So this works for me because I can still either apply the quadratic equation or I can use the zero product property. And so because my last term is a negative, I know I need one of each sign. Because the middle is positive, I know the larger factor is going to have to go with the plus sign. And the only way I can get 3 multiplying factors is 1 times 3. So just got to make sure the larger number goes with the positive side, and then just double check that big smile gives me 3x and little smile gives me negative x, and that together gives me positive 2x, which is what I have here. So I've factored this thing and figured out that if I set each one of those equal to 0, I get x equals negative 3 and x equals positive 1. So my two horizontal intercepts are going to be the points negative 3 comma 0 and 1 comma 0. Those are my horizontal. What do we mean by horizontal? The horizontal axis, which is more commonly thought of as the x-axis, but we can use other letters than x, and so it's more generic or general to use the word horizontal here. But those are my x-intercepts. So negative 3 comma 0 and 1 comma 0.